This conference will now be recorded.
Good afternoon, everybody. We'll give it maybe 1 or 2 more minutes, as I see we've still got people joining us from wherever they are in the world.
How you guys write emoji? Mo, MG. Hmm? Oh, okay.
Okay, I think we can get going. I want to thank everybody for joining us here today for a few presentations about the NOPP Hurricane Coastal Impacts Project. My name is Alan Leonardi. I'm the, excuse me, and I'm the director of the National Oceanographic Partnership Program Office, or NOPP as we commonly refer to it. And I'm going to be your MC and moderator. I'd like to start by first handing the microphone over to Alex Kuropov. In case, Alex, you want to share some comments, and thank you, of course, for letting us piggyback on the seminar series for these past 5 weeks.
Oh, Alan, thanks. Good afternoon, good morning, whatever your time zone is. I just want to express gratitude to you guys for running this so smoothly. We learned a lot of young people here in the audience even today. Unfortunately, this mini series comes to the end, to the completion. So no easy life for us. But next week, guys, for those of you who follow the coastal ocean modeling seminars, we'll have the regular seminar now. So wait for the announcements and check the calendar. And again, thanks to the NOPP and thanks to all the speakers in this series. Looking forward to seeing what's today. Back to you.
Great. Thanks, Alex. The National Hurricane Coastal Improvement Project that will be discussed as part of this series that's been going on for the last 6 weeks, a 5-part series, is supported by the National Oceanographic Partnership Program with primary funding from the Office of Naval Research and the National Oceanic and Atmospheric Administration. As I've said, today's discussion is the 5th in the 5-part series and will include 2 presentations. The first presentation will be given by Rick Ludick from the University of North Carolina at Chapel Hill. And that will focus on predicting coastal impacts from tropical cyclones using the ADCIRC prediction system. And the second presentation will be by Maitani Olabarrieta from the University of Florida, with contributions from Arthria Subgranon, also at the University of Florida, and John Warner from the U.S. Geological Survey. That one will focus on forecasting hurricane hazards and impacts on U.S. East Coast and the Gulf of Mexico specifically. Each presentation will last approximately 30 minutes, including a 10-minute question and answer period. So for ease of discussion using this virtual format, I would ask that you refrain from asking questions until the end of each presentation, where I will attempt to moderate the Q&A, both in the chat and anybody who would like to open their mic and ask a question. I'll now hand the virtual microphone over to our first speaker to get the conversation started. Rick, the mic is yours.
Great, thank you. Let's see if I can get shared here. All right, does that look good?
Fantastic.
All right, well, thank you so much for the opportunity to present our work as part of this wonderful NOPP project. This is work that has been done with my colleagues here at the University of North Carolina at Chapel Hill, Zach Kobel at the Water Institute. Zach is really our systems guy, as well as somebody who's run a lot of the actual forecasts I'll tell you about. Nasheed and Matt Bilski at the University of Georgia, who've done a number of things, but I'm going to show some ensemble work that they've done. Angelos and Tetsuhara and Isaac Guinness at the University of Rhode Island have done a lot of the wave work and wave current coupling I'll tell you a bit about. Jessica Gorski and now Narumi and Casey Dietrich at North Carolina State have done the X-Beach work I'll show you a bit of, and Sebas, Mashad, and Dan Cox at Oregon State have done the damage work that I'll show you a bit about. And I just want to point out that we've had a number of students and early career folks work on this. John Ratcliffe, as a student in my group, is now at NOAA, so he's transitioned. Jessica is now at the USGS St. Pete. Sebas is at Ancora QEA in the private sector, and Mashad, who is a postdoc in the project, is now an assistant professor at URI. So in addition to knowledge and the accomplishments of those, it's been great to help to see these young folks get started and be part of this project early in their career. Our objectives really were twofold: develop a forecast system using NRLs or the Navy's COAMPS tropical cyclone forecasts and other data that's provided by other partners in this NOPP project related to DEMs and land cover and all. And do this with our ADCIRC plus SWAN system, couple in X-Beach, and get to damage evaluation, because ultimately it's coastal impacts as the CI that are in this project. And so we've been using FEMA's HAZUS damage evaluation program for that. And then secondly, and quite importantly, is to understand what it is we can do with these forecasts, at least in terms of their skill, the processes that are underlying what is going on. And we have had wonderful data provided as part of this project, both from land-based deployments, but drifting buoys. And we got to see some of that a couple of seminars ago. And of course, there's other meteorological, hydrodynamic, morphological data available. And then as part of this project and complementary work, there's a huge amount of damage data that was collected with Ian that I'll show you a little bit about, that I think is compelling and adds a lot, both in our understanding as well as where we might be going in the future. So most of what we've done is related to Hurricane Ian. It was kind of the first major event that we did predictions for, and so I'll walk you through some of that. We also did Adelia, which was last year, and I'll show you a little bit of that, and then there's some additional activities I'll touch on at the end. So Hurricane Ian, we received forecast from COAMPS TC forecast, gridded wind fields every hour for a number of forecast cycles throughout the length of the storm. And this is just the track and intensity plots. Again, if you joined for the first seminar, you heard a little bit more about that. We grabbed that data, started to use it as forcing for our models. And here's a little bit of an animation of the wind fields. You're going to notice something, that every few time steps, the wind field changes dramatically. Right there. Right there. So this was interesting, and we wondered about this. What this is this is not a single forecast. In order for us to have an initial condition for our hydrodynamic models, we have to spin up, we have to do essentially a nowcast, and so we have to spin things up to the present time, and then of course we do a forecast from here into the future. Well, to do that, we would go and take the COAMPS runs and string together kind of 6 hours at a time, 6 hours between the cycles. So every 6 hours, we would pull out the first part of the COAMPS file, string them all together, and then we could use that as kind of our best available meteorological forcing to do a nowcast with. What we learned is that, and we do this routinely with GFS and non-tropical for non-tropical events. But what we learned is that that the way in which COAMPS TC is initialized every 6 hours, it takes a couple of hours for it to dynamically adjust. And so on the right-hand side now is the same animation, but it's if we skip the first couple of hours of each COAMPS TC cycle and then string things together that way. So As we've done this project and worked with these gridded wind fields, this is one of the things we've learned as we've gone along. It begs the question as to whether using other TC models for forcing for hydrodynamics would have a similar problem. I know they have different initialization strategies. So this is one of the things that we're interested in looking into in the future. But having figured this out for Ian, it seemed like skipping the first 4 hours in the cycle was optimal and gave us a good both validation of winds and the surge. I'll show you a little bit of that in a minute. We ran on a kind of a typical ADCIRC configuration of the Western North Atlantic, Gulf, and Caribbean. Resolution in the Fort Myers-ish area. What you see in the lower right-hand corner of the inset is Sanibel Island, Acero Island to the east of that, and then Fort Myers area in between. With the latest topobathy, we could grid and get both the water and the land parts fairly well resolved, down to about 200-meter horizontal resolution in this case. Here is not a forecast, but actually when we string together essentially all of the forecasts, skipping the first 4 hours, put them all together and do what I'd call a pseudo hindcast. And this is just a composite from different areas. The upper left-hand corner is kind of the big zoom out from Tampa all the way down to Key West. You can kind of see how the storm came ashore, and then there's 4 locations that give you time series. The gray is observations and the blue is model. So it tracks pretty well at the large scale. And then the other 3 are insets. If you look at the upper right-hand corner, that's really the major impact area. Again, Sanibel's on the left, Acero's on the right, and Fort Myers and Cape Coral up in between. And you can see it'll come back around one more time. You can see substantial inundation, inland inundation. And even in the lower right-hand corner, there's observations that are inland, and you can see that we've captured that pretty well also. So we were pleased with how with that capability. And here's just some kind of a scatter plot of high water marks. Again, not too bad. If anything, we underpredicted some of the highest water levels, which were out along the outer barrier islands, and maybe infragravity waves, which we don't include, but overall, not too bad for a fairly complex region. I mentioned that we were doing waves, and again, the project dropped buoys out in front of the storm, and you can see up in the at the top tracks for the various drifting buoys that we had available. If we bin those and computed significant wave heights along the track over time, we can do a scatter plot between our model and the observations. And so the right-hand side shows ADCIRC plus 1. The left-hand side, we also ran ADCIRC coupled to WaveWatch 3. You get a little bit of a different picture. WaveWatch 3 tended to underpredict the highest wave heights, significant wave heights, and there was a bit more scatter in the results. Swan possibly overpredicted a little bit, but in general they were close with that caveat. Now they did use different physics packages, but it's not clear that that is the root of this. They may actually be calibrated to different wind strengths actually. As I mentioned, we did X-Beach runs. These were one-dimensional X-Beach runs. These are a series of forecasts through that time. Landfall was on late in the day on the 28th. So this is 5 days up until post-landfall in southwestern Florida. And this is distilled down into green was no overtopping of the dunes, and red is overtopping of the dunes. And so you can get a sense of how that progressed over the course of time. And also what's oftentimes forgotten is that Ian had a second landfall in South Carolina, and there was significant dune overtopping associated with that part as well. This work actually has been written up and is in review for publication. So many more details are available if you're interested, and will hopefully be published soon. I mentioned we went all the way to damage and used the FEMA's HAZUS program. Our results were a little bit underwhelming in terms of us getting damage estimates in the $2 to $3 billion range. By all media accounts, that was maybe an order of magnitude low. We have dug much more deeply into that. And again, the group at Oregon State has been part of a much broader community that has been out and taken extensive video and photographs of essentially every single building out there, particularly here on Acero Island. Back in the computer lab, analyzing these to assign damage states. And this whole process is now in a paper that's under review. But on a building by building basis now, we have damage information associated with Ian for this area. We can import our model results. This is inundation depth above ground, maximum depth above ground, but we have a similar layer that we can do with maximum significant wave height. And then using a damage algorithm that Tom Zeck published about in 2014, it's encouraging, the sense of our ability, I think, to predict which buildings were at least reasonably, the damage state of the various buildings. Again, there's a lot more, I think, to be done in this area, and ultimately, hopefully getting this knowledge back into the damage algorithms that these large-scale programs like HAZUS work with, but very encouraged, and another manuscript that will be submitted shortly. And also this data is being more broadly used by others in our project as part of their efforts as well, and we're happy to see that happen. Lastly, for Ian, we've looked at ensembles. Everything I've showed you to this point were deterministic runs, either forecasts or pseudo hindcasts. But COAMPS also has a 21-member ensemble, and they gave us the gridded fields for that for 2 different forecast cycles. One on the left is about a little bit less than 2.5 days before landfall, and the one on the right is about 1.5 days before landfall. We can these are just a postage stamp of all of the maximum wind speeds. So you can see that not only is the track location varying, but also the intensity changes as you would expect in the ensembles. We can compute maximum water levels for each of these sets of ensembles, and then get to exceedance surfaces. So for these 2 forecast cycles, on the left-hand column is the 10% exceedance surface. So there's only a 10% chance water levels would get higher than what are computed here. And so again, you got a sense the areas of where the Fort Myers area certainly lights up in both of these cases, more so in the latter, in the 1.5 days out. Of course, the track was more focused. So that's encouraging. The depths were, at least along the open coast, comparable to what we observed. We've been looking a little bit more carefully at gauge locations, and this shows the gray line is observations, one up in the Caloosahatchee River in Fort Myers, a NOAA gauge, and then the second out at Naples in a more exposed area. The gray is, again, those gauge values, and the individual lines or the individual time series that came out of the model results. You'd kind of like to see those that the envelope of those time series, encompassing the entire observational values, and they don't. In the Caloosahatchee, they're a little bit closer in Naples on the open coast. So it's not altogether clear, but it may be that this ensemble isn't sufficient to actually give you statistics that are actionable. Again, I think a lot of this remains work in progress, but nevertheless, it's interesting to see how, as we try to move towards ensemble and statistical results, how this sorts itself out. So that's just a brief thumbnail of Ian. Adelia, again, we had gridded wind fields from COAMPS TC. Here's a postage stamp of kind of all of the forecasts we were working with. And so again, it was a much better, it was much tighter forecast over the sequence of forecasts. And you can see they all pretty much come into the Big Bend area. This is maximum wind speed. And so very similar throughout the several days prior to landfall. The maximum significant wave heights we computed for these same times all are relatively similar, and the surge as well. We've done validations on water levels, but and then lastly, we've got X-beach results also. In this case, the yellow is overwash and the green is not. And the sandy, beachy areas really to both the left and right of the track were anticipated to overwash, predicted to overwash in pretty much all of the forecasts. As I said, we've done water level and wind validations, but what I'd like to do, since we had this amazing set of buoys that were dropped in front of the storm, that the storm cut a path right through the middle of, show you a little bit of the wave results we have. And in this case, the upper left-hand corner is the winds. So you'll see that move along the track in a minute. The buoy that we've analyzed is that little squiggle that comes off to the west, and the red dot will track along. You'll see that move along to the southwest as it goes. The below that is the spectra that is computed from the moments that the buoy collects. So wave spectra. And then in the top right, in the middle, in the top panel, in the top row, in the center column is the spectra from SWAN, and in the right column is the wave spectra, directional wave spectra from WaveWatch 3. So all of these will advance, and so you'll see the storm kind of work its way in. The spectra you'll see how they advance. And in this particular buoy, you can see the observational and the model spectra aren't bad. They're pretty close. It's going to start over again, and then we'll run to the end. But in this case, they seem to be reasonably well captured by the model. If we look at bulk parameters over on the right-hand side, the buoy is red, SWAN is black, and WaveWatch is blue. They're pretty close. Again, SWAN tends to be a little higher, a little bit more energy than WaveWatch, but in this case, a pretty good agreement. And I'll just show you one other now. This is another buoy. This buoy is going to go right into the eye of the storm. And so you can watch it again as the storm progresses towards a collision, if you will. I just stopped it. Again, look at the spectra from the observations and then the two models. Directionally, pretty similar. And just for orientation, this is the direction the waves are moving towards as opposed to moving from. So there is more energy, it appears, in the model spectra than perhaps in the observational spectra. But one more time. And then what I'd like to do is stop it just as the buoy gets into the eye of the storm. And you really start to see at this point that the spectra start to deviate a bit, a lot more energy in the model. And in fact, even the directions have started to wrap around in the observations. So we suspect in this case, there's so much data and it's so granular that we're now in a really high gradient area of the storm itself. And just relatively small location errors in where we think the storm is might account for this. If we jump to our bulk parameters, you can see that both SWAN and WaveWatch 3 way over predicted the significant wave height. And so, again, it's not clear that that is the models per se, but rather probably has to do with the collection of, the forcing as much as the wave models themselves. And lastly, one thing we noticed, you'll see all of these, this is back to the maximum wind fields, you'll see all of this sort of spring looking character to these. We had hourly output fields, and this is a fairly fast moving storm. And so we wondered the extent to which that large time increment might be affecting our results. And so the NRL guys gave us results at 15 minutes and 5 minutes also for one of the forecasts. And we were able to redo the water levels and the waves. And if you do a difference plot between them, in particular, if you difference the hour with the 15-minute, you see that it makes up as much as a 10 meter per second difference in wind speed in some areas. That's the deep blues in the left-hand column. About a 30 centimeter difference in water levels in some areas in the center column, and plus or minus a 30 centimeter difference in significant wave heights as well. So based on this, we have concluded that probably hourly output is okay for forecasting, but in the future they're going to give us 15-minute output for reanalysis. And then lastly, I'll just mention kind of 4 additional activities. We did an early study on Hurricane Michael, kind of the first year. It was a hindcast because it had already existed, and found some fascinating results as to the role that advection played in the surge in Hurricane Michael, as much as 3/4 to a meter of difference in surge, depending on your use of advection. Many models do this, although surge models have tended not to, and for example, the slosh model doesn't include this, but paper that just came out last week that encourage you to look at if you're interested. Again, our URI folks have been working on enhancing the wave current interaction that's in ADCIRC. It currently does radiation stress gradients, but about 15 years ago, the Lagrangian effects were also worked out, and they have included that in ADCIRC and have a paper that's in review in JGR Oceans, again, if you're interested. And then recently, a couple of weeks ago, we did quite a number of forecasts for Hurricane Beryl, 26 with the COAMPS, 30 with NHC advisories, and 5 using the new HAFS model, the Hurricane Analysis and Forecasting System models that have come out of the National Weather Service. And so we're interested particularly about the initialization issue in HAFS, whether it is similar to the initialization issue that we found in COAMPS. And then just lastly, I'll put in a plug for this thing we call MetGet, which has, for us, revolutionized access to meteorological models. It's a single interface that we've built and a single protocol for accessing almost all of the meteorological data that's out there. We haven't got ECMWF access to that, but others, and so it makes it very easy with a plug and play to move between the meteorological models. And this has become this is an open community resource, and the Deltaris group has been using it, and I think Matani's group is moving in that direction as well. So happy to do that. So with that, I will say thank you and acknowledge NOPP's funding, but also some of our partners. Clearly, this leveraged a lot of other resources as well. Thank you.
Yeah, thanks for the presentation, Rick. Very informative. We would typically do questions after each of the presentations, but I think given the time, I think maybe we'll jump right into the second presentation led by Matani, and then we'll combine all the questions for the presenters at the end. That'll probably be the smoothest way to do this at this time. So Matani, the floor is yours.
Thank you, Alan, for the introduction. Let's see if I'm able to put this in presentation mode. Here we go.
You run the low-res WCDA test case. Does the Hurricane task runs the first cycle?
I can hear some voices there. Here we go. Thank you very much. Good afternoon, everybody. I first want to say thanks to Alan for the introduction and Rick for introducing all those hurricanes to us. In this talk, together with Artria Subranon, we will give a description of the efforts of the coast modeling team within this project. Okay, so our main goals within this project, the Hurricane Coastal Impacts, is to build and apply a forecasting system to forecast water levels, currents, waves, but also the impacts on infrastructure, sediment transport, and morphological changes. As you will see later on in the presentation, we have done a lot of effort actually like on impacts to infrastructure. We have a new module now, and that's what Artria will explain in the second part of this presentation. We have to provide a daily forecast of hurricane coastal impacts starting 5 days prior to landfall. And as Rick said in his presentation, in this project, we have this amazing opportunity of having access to all these data sets that are being collected within the hurricanes. And with those, we can verify our water levels, the waves, and also the impacts. And we can try to see where these predictions like fail, where they succeed, and try to improve those predictions and forecasts. Within our team, we use the coast modeling system, and this system couples dynamically the ROMS model, the regional ocean modeling system, with different wave generation and propagation models such as SWAN, WaveWatch 3, and we have InWave as well. And now we have this new module that it's called BuildForce, that its aim is to predict these impacts on residential buildings. In this project, we use Quantitative as the forcing source. And how do we differentiate from, for example, like Rick's group and Van Dongeren's group? So the main difference is that we solve the baroclinic structure of the oceans. We solve the major like oceanic currents and the 4-dimensional structure of the flows. We include wave current interaction, and we have several wave-dependent ocean roughness parameterizations. And now we use machine learning to basically predict the damage on infrastructure. We use this cascading or telescoping nested grid approach in which we resolve the ocean dynamics and wave dynamics in a grid that covers the Gulf of Mexico and the US East Coast at not very high resolution, about like 4 kilometers. And depending where we expect to have the impacts of these hurricanes, we downscale to each of, well, to a grid, an L1 grid that has a higher resolution, about 1 kilometer. And then we have higher resolution and more local grids in which we can increase the resolution. And at the end, we can go to resolutions up to 5 or 20 meters, where we can resolve, for example, infragravity wave dynamics and sediment transport processes and morphological changes. We have applied this modeling system in hindcast mode within this project. Hurricane Michael is an example of that. And also in forecast mode, Hurricane Ian, Idalia, Lee, and Beryl. And I'm going to show you 2 examples, one in hindcast mode and the other one in forecast mode. So the first one is Hurricane Michael 2018. This Category 5 hurricane made landfall in Mexico Beach, that is located here in the Panhandle, and it created like devastating consequences, this hurricane. It also created a new bridge in Cape San Blas, that is this cape over here. And we were wondering if with our modeling system, we were able to reproduce the formation of that bridge. And this is the work primarily led by John Warner. So basically he set up the whole system in the Gulf of Mexico, in the Florida coast, west coast, basically, and ran ROMS and a WaveWatch 3, verified the water levels, the directional wave spectra, and obtained the boundary conditions for this very local grid, where he activated the sediment transport processes and also the infragravity wave module. So here on the right-hand side, what you see is the result of InWave. It's our infragravity wave module. And what you see is the significant wave height basically changing at this wave group scale. And that forces the water level oscillations that you see on the top. That includes the effect of those infragravity waves. Now, if we look at the morphology of this barrier island before the impact of the hurricane, that's on the top. We have the aerial imagery and also the morphology of the barrier island. Basically, the dune structure before the hurricane. And in the lower part, we see the situation after the hurricane with the bridge already opened. And then on the right-hand side, you see the morphology resulting from coast for two different simulations, one without considering the effect of the vegetation and the other considering the effect of vegetation. And what we can see is by including the effect of vegetation, the morphological change basically in the upper part of the barrier island is diminished, sediment transport is reduced, and the bridge that we get, it agrees better with the observations. The team led by Dean Gesh has put a lot of effort on creating this high resolution and also digital elevation models. So these are, we think they are necessary to predict this kind of impacts. Now, when we get into the forecast mode, things get much more complicated because we have many other sources of uncertainty. And one of the main sources of uncertainty are the atmospheric forecasts. And Hurricane Ian, I thought it was a perfect example to show you how this uncertainty in the atmospheric forecast translates into uncertainties in oceanic forecast. And I will also take advantage and show you how we operate before, during, and after hurricanes in this specific example. So as Rick explained previously, Hurricane Ian made landfall in Fort Myers as a Category 4 hurricane and also created devastating consequences, as you can see in these two images. So basically how the overall team works in this project is before the hurricane, we needed to be ready to get observations, but also to forecast. And if we see during the hurricane season that an atmospheric instability appears, John and Jim Doyle from NRL, they keep us updated about how that instability is going to, how they think it's going to progress basically, and which is the probability of this instability of becoming a tropical cyclone. We are also in touch with Athena Clark and Jenna Brown from USGS. They keep us updated about the plans of the storm response team. And there is a continuous communication between the project, the different team leads basically, to decide whether we are gonna take that tropical cyclone as the hurricane to work on. And that has to happen pretty early, at least 5 days prior to the expected landfall, because Jenna's team has to go and deploy her instrumentations, and that takes time. And also task 3 teams, they needed to go and fly and throw the drifting buoys. So that takes a little bit of time. And for example, in Ian, there was a big uncertainty of what was gonna be the track of the hurricane and its intensity. And that makes our life a little bit more difficult. And it depends from hurricane to hurricane. So for example, in Idalia, this uncertainty was much smaller, but in Ian, it was very, very big. So one of the things that we do within the project, once we have decided that we are going to work on a specific hurricane, is we use a particle tracking model to predict where those drifting buoys will, basically how they will move, what's gonna be their track. Because what we don't want is to deploy those drifting buoys and that they are taken away from the zone of interest by oceanic currents, for example, and we don't want those to make any to get to beach areas because they will stop measuring. So we use this what it's called ROMS path. It's a particle tracking model developed by Eli Hunter, and we use John Worsner's coast forecast to determine where we expect those drifting buoys to, how we expect them to move. And if we see that they are getting out from the area of interest, what we do is we again change the drop locations and we iterate, and together as a team, we decide where to drop those. And we also help with the deployment of those buoys. Here we can see John Warner and Marta just getting ready to take a flight to deploy those sensors. Okay, so getting back to the uncertainty, we work with the deterministic forecast, and our team takes one forecast daily, and we focus on the C00 forecast coming from NRL. Here you can see the comparison of the best track of this hurricane of Ian in blue, and in orange you can see which is the track or the path predicted by this specific forecast, the 26. The 27, we see that both the models and the best track are a little bit closer, but there are differences in the intensity. And then as we approach the landfall moment, usually we get a better agreement between the tracks, but still we may have differences in the intensity. Okay, as Rick explained before, and as other seminars have explained, here in this project we have this amazing data collection of drifting buoys. These were the observations that were collected during Ian, and I'm going to show you the comparison of our forecast for two specific tracks that were closest to the best track of Hurricane Ian. So here you see the comparison at two of those locations. So here in the top, as we can see, the different forecasts are giving us different timing for the maximum significant wave height, and it also affects the intensity of that maximum significant wave height. And we can have up to 2 meters of difference from forecast to forecast. And well, what this comparison show is that what it looks like, these forecasts were not that bad. Like the track, it's not that far away from the best track, but still for us in the ocean, these results in big changes in our maximum water levels. I'm not showing it here, but also in the significant wave heights. And if we compare especially which are the differences, as we can see here, between these two forecasts, the 26 and the 28, the differences in the significant wave height are very, very big and very dependent on where that track of the hurricane is located at. What we usually do is after the hurricane, NRL creates a reforecast. That means that they reforecast this hurricane, and they basically correct the path of the track of the hurricane and also its intensity. And that's what we are seeing here in the left-hand side. We can see how they observe the best track, and the model now is in better agreement. And the same for the intensity of the hurricane, and we repeat our forecast. So here I'm showing you the results of SWAN for this reforecast, and again we still can see that there are differences in the maximum wave heights that were measured and the ones that we are modeling. Basically, what is happening here, and this reiterates what Rick explained before, is that at this point, when we are at these very high wind speed conditions, small changes in the structure of the hurricane and in the estimation of those wind speeds basically can result in significant changes in our model results. So it is very difficult to ascertain whether this is coming from our models, from our closure models, or if it is due to basically not getting the perfect picture of those wind fields. And that's what we are working on together with task 2 and task 3 on trying to put all the information together to see if those errors are coming more from our models or if they are coming from basically uncertainties in the atmospheric forces. And all these uncertainties now they fit into what Atria will explain, that is the forecast damage in infrastructure. Atria, please.
Yeah, my name is Atria Safranon, and before I get started, I also like to acknowledge my PhD student, Stephen Kapak, who has put his effort in developing these damage prediction models. Next slide, please. Wait to me. Sorry. Okay, so the goal of our task here is that we want to be able to make the prediction on the potential damage that we can have on the residential buildings that got affected by the hurricanes. And for example, you can see these two houses, both of them are impacted by Hurricane Ian. And from the original condition that we can see from outside, they look pretty similar. But once we, compare the damage right after the hurricane, we can see that one house suffered more of structural damages, while the other one just suffered from the minor damage. So we want to be able to take information on the hazard information, the building information of each individual house, and also the surrounding of that building in order to make the prediction of the potential damage that the houses can have. Next slide, please. And just to give a bit of background comparison between existing models, and I think HAZARS has been used a lot, and that's introduced by Rick as well in the previous presentation. That's coming from FEMA. And for the HAZARS model that's available there, they usually assume distribution of the archetypes and then make the prediction with the target that they make prediction at the census tract level. But for our models, which is called the build force, it stands for the building damage forecasting of the regional coastal event. For our models, is driven by the data, and we use the data that we collect from the past hurricane in order to train the machine learning models. And we get information in terms of the attributes of the individual houses that we are looking at. And for the hazard, we take a look at the gust wind speed relative to the design wind speed at that house, and also the inundation relative to the first floor elevation of the house, and then we make the damage prediction. And because it's the data driven, so it also have the potential to be able to improve as we have more data collected. And this is just give, next slide, please. And this gives illustration of the output that we can have from our models. So as I said before, the target is that we want to be able to make the prediction at the building level or the parcel level of the individual house. We want to be able to get the output in terms of the damage states at that house. And what you can see in the big figures here is that the small dots with different colors representing different damage states at the individual houses in the impact area, as compared to the existing model in the smaller figures that's coming from HAZARS, which is give information at the census tract level. Next slide, please. And this is just to give information on how we define the damage states for our models. We take it from starting with the HAZARS classification, where they have classified the structures into 5 damage states, based on the levels of damage that we can see on different components of the house. And then we did some consolidation, so we end up with 3 damage states that include no damage at all, or just non-structural damage, and then the final one is the structural damage. And that should give enough information for evacuation planning or planning for the first responder to be deployed in that area. Next, okay. And this is information on our machine learning approach. We use the random forest classifier models as our machine learning method. And we train this model using the data from the past 4 hurricanes, Michael, Laura, Harvey, and Irma, with about 2,500 houses. And then we take 80% of the samples for training, and then another 20% we use that for testing our models. And what you can see on the tables on the right, that's showing different features that we take as an input in our models to make the prediction. And there are different types of features that we include, and that include the building information. We have the hazard information in terms of the wind speed, wind gust, and also the inundation depth relative to the first floor elevation. We have geospatial information, explaining the natural and also the built environments around the building. We also include the socioeconomic status of the household, and also some strategic information that kind of relate the hazard into the damage states. Next slide, please. And this is the result from our first version of the models. On the left-hand side, we can see 2 confusion metrics that's showing the the ground truth of the different damage states versus the prediction. And the goal is that we want to have the darker colors on the diagonal, which means that the prediction is actually aligned with the ground truth. and we compare, our model's machine learning approach to the hazards model. And we can see that for our machine learning model, it has about 76% accuracy versus 47% from hazards. But that's also because hazard was target for the, census tract level, not particular for the individual houses prediction. And on the right-hand side, that is showing how additional data can actually improve the models. And we start from just using the training of the data from 1 hurricane to 2 hurricanes, 3 and 4, etc. And then in the dashed line, that's our model performance, which we can see the increasing trend, which means that as we have more and more reconnaissance data to improve the model, we can improve the performance. And in the solid line, that's showing the hazards, which does not really improve with the data because it's not a data-driven approach. Next slide, please. And these just give, the flow of our modeling. So as the hurricane is coming, first thing that we want to check is that we want to check if we have the columns wind information or not. If we have that, and then we go ahead and check if we have the building inventory in that area. If we don't have the building inventory, we need to get the building inventory in that area. And then after that, we check for the water levels information from coast modeling team. And if we have all of that information, we can make a damage prediction using our already trained machine learning models. If we only have the wind and the building information, we can also make a prediction with another models that based on just the wind and the building information and make like the water information. And then we can run the models like that. Please. And as we transition into the forecasting mode, one of the challenges that we have is that we need to get the building information really quickly. And the information that we use for our trainings is coming from really detailed appraisal information from county to county, and that can take time to collect. So we decided to use the AI approach based on the building recognition in order to extract the building features directly from the Google Street View or the satellite images. And that can be done really quickly within a few hours, so that can be done as the hurricane is approaching. And for hazard information, we take the input that's coming from the columns, wind, and also the coast modeling team to give the water prediction for our hazard information. Next slide, please. And another models that we need to develop is actually to predict the first floor elevation, because that's really important parameters to use in estimating the damage due to flooding. So what we did is that we also use the AI approach, and then we can use the object detection in order to detect the door, the first floor, and then try to calculate the first floor elevation of the houses from the Google Street View. Next slide, please. And this is just showing the validation of our first floor elevation models. And that one, we compare that to the elevation certificate, which is the ground truth of, elevation of the house that we looked at. And then we have the two data sets, one's from Florida, the other one is coming from Virginia. And from what we've observed is that our machine learning models doing quite a good predictions. On average, we have less than about 5 meters in terms of the errors that we have. And then it's actually even outperform the information estimated from the National Structure Inventory, which is based on the assumption on the foundation type, and then try to make the prediction of the first floor elevation. So once we know that this machine learning approach is working well, and then we implement that in our machine learning algorithm so that we can get the first floor elevation estimated before the hurricanes come as well. Next slide, please. And this is the case study that we have on the Hurricane Ian, where we operate in the forecasting mode. We have about 15,000 houses that we get inventory in that area. For the data of the hazard, we got from Cohen Screen and Coast Modeling team. We use our View Force model to make the prediction. And as of now, we have the validation just in terms of the qualitative one based on the preliminary report that we see from the impacts of that Hurricane Ian. we found that in the coastal urban area, more inside into the coastal, it makes quite a good prediction, comparing to what we see on the report. But we still have the challenge to make the prediction on the barrier islands area, in particular in the Sanibel Island. We might be a bit over predicting, while in the Fort Myers Beach, that's a bit under predicting. And that can come from many reasons. We have uncertainty in the hazard modeling that also propagated through our damage model. We also need to improve our models in taking into account the vegetation landscape. If we have mangrove in the Sanibel Island, and that's going to help alleviate the impacts of the hurricanes to the houses. And we're working on improving those models. And we're also waiting for the full data set from Oregon State University on the reconnaissance, so that we can actually make the quantitative validation of our models to all the houses in that area. And that should be coming soon this year. And that's what I have, and then I'll turn it back to my team. Thank you.
Thank you, Artelia. That's all from our side. Our acknowledgements to all our collaborators and the developers, and we are ready to take some questions.
Great. Thank you. Thank you both for the presentations, and Rick for yours as well. We'll open up for a couple of questions. We're near the top of the hour, so I am sensitive to that. We can hang on for a few extra minutes here in the NOPP office, but others may need to drop off. So if folks need to go ahead and ask questions, they can feel free to put them in the chat, or you can turn on your camera and I'll call on you. We do have one question in the chat already. From Phil Miller. He's got a couple of questions, one for Rick, which is regarding the analysis of Met forcing, the delta T equals 60 versus 15 minutes, showing 30 centimeter differences in total water level. I'm hoping you can read this, Rick, because there's a lengthy question here. Knowing the error is present seems questionable to accept for forecasting usage, given the presence of threshold effects and the consequent impact and the need for hazard forecasts to capture distribution tails. The question really is whether you could elaborate further on the rationale in this case and whether there are other considerations that Phil might not appreciate.
Look, this is definitely an optimization problem, if you will. There are big data files to push around, how quickly you can get them. And recognize the forecasts themselves have quite a lot of inherent uncertainty, with the tropical cyclone intensity and track and all of that. It may be as different sources of errors can be reduced. This just seemed like again, an effort to kind of optimize things. In an ideal world, we'd be down to, we'd have much more frequent output. At this point, in terms of us asking our NRL colleagues to package up data files and send them to us, it seemed like hourly intervals was adequate, again, for the forecasting. But when we do the reanalysis, when we're really trying to dig into the processes and whatnot, then we wanted the higher resolution, so we could at least eliminate that as a source of error. And going forward, I wouldn't argue that perhaps we can do better with the forecast time intervals. Just a judgment call, really.
Fantastic. Thanks, Rick. And then there was also a question for Atia, and that was whether or not the building construction year, or like one of the features, had to do with building codes and practices. Yep.
Yeah, the building construction year is also included as one of our features. So for our first version, where we train on the reconnaissance data, because we get really detailed information from the appraisal from county by county, we have specific year to train our models. But once we transition to the forecasting, we need to work with the information that we can extract from the photos. And in that one, we still including the construction year, but instead of year by year, it's more break up into the era. So like aggregate into the 10 period era. And we're still investigating how the accuracy of that prediction is affecting the performance of our models. But yeah, we include the construction year as one of the features.
Great. Thanks. And just a comment from Jamie Pringle. A lot of thanks for everybody. Jamie's working as part of a related EPSCoR project in New England on flooding, so this has been a really valuable series. We appreciate that. I definitely agree it's been a valuable series. We've got a comment from Behzad Nazari, just thanking for informative talks. Asking if there's been any steps taken for parameterization from the wave to hydrodynamic to the sediment transport model, where challenges for all the parameters may be required. I don't know who might want to take that, but.
I'll just confirm there's a lot of parameters. Each model you tack on, you've got more parameters, and this morphology model has certainly their share. We have tried to run them with sort of the standard recommended out of the box parameters, if there is such a thing. And we have, but you know, sediment characteristics and other things definitely, and vegetation in particular. Matani pointed that out in her talk nicely. Those all matter, and so the goal is to get them right in a process-based sense, but recognize that we have limited access ultimately to a lot of the data, so we do parameterize.
Great. Any other comments from any of the other speakers on that topic? Okay, well, I know we're at the top of the hour. People have busy schedules. So I just want to say, yeah, the comments from Phil Miller were a thank you to everybody for their answers, as well as from Behzad, thanks. They used the same approach. I personally just want to thank everybody for joining us today as part of the NOPP Hurricane Coastal Impacts Forum, but also for those who have joined us throughout this entire 5-week series that we've had going on over the last month and a half. A special thanks goes out to our NOAA partners for allowing us to piggyback or even co-opt, you might say, on their normal seminar series, which I encourage you all to pay attention to, because they will get back up and running again as usual next week. I also want to thank the entire NOPP Hurricane Coastal Impacts project teams for pulling everything together and helping make everything run so smoothly. The presentations were all extremely informative and helpful. I personally got a lot out of them. I hope that others did as well. But before I close, I also want to say that I would be completely remiss if I didn't thank the agencies, especially the Office of Naval Research and NOAA, for the funding that made not only these efforts possible, but for the funding that makes the NOPP office possible so that we can help bring these things to you. In the coming weeks, we hope to post the session recordings online at the nopp.org website, www.nopp.org, and we hope to see you all again very soon at forums that might be coming in the future. Thank everybody, and I hope you have a wonderful day.
Thank you.
Thank you. Thanks, everyone.
Thank you.